Good evening, everyone. Let's get into it. Just wait for this countdown to start. The official timer of 6771. Oh, wrong thing. Hi, good evening, and welcome to COMP6771 for week 3. I hope that you all enjoyed your long weekend day yesterday and one less lecture to put up with this week. Today we have this week we only have 2 hours of lectures. One thing that's really helpful about this course is that when it was originally, when me and another person rewrote it in 2019, the uni screwed up and only gave us 3 lecture hours a week. So the course was actually originally written for only 3 hours of lectures a week. So that takes a little bit of pressure off us. But we've used that time to fill it with other things that we didn't have there before. I think before we get started, I don't really have any broad updates. I think probably just the only thing is that essentially what will happen is that we will take your assignments on Sunday evening, which is when the last people can submit. We will auto mark them, and I think just as a heads up, auto marking will take a while. To auto mark all of you will probably take so here's the thing, we've got, say, we can all do this really quick just because it's interesting. Let's say we've got 450 students and we're going to have, say, about 50 tests. I can't remember, and each test will take up to 15 seconds, but let's just say an average of 5 seconds or something, or whatever, because not all of you will need 15 seconds on everything. So that's every student. We need 5 whole seconds, and then that's that many seconds. And 50 tests. I probably screwed something up. Anyway, the main point is that it will take approximately a day or two to mark. I think I've done the math wrong, so this wasn't very exciting. But it will take quite a while because some of you have really slow tests. Oh, that's per minute. Oh, I see. I thought that was per second. So yeah, 37 hours sounds about right. I did it right. It's due on Friday, but we can't mark it till everyone's submitted because there's late submissions. That's why I say Sunday. So I'm just managing your expectations early that I can't start auto marking until Sunday night, and then once we auto mark, it'll take us 2 or 3 days just for the auto marker to finish because of the amount of time it takes, and then we'll get your tutors marking it. And I'll ask them to try and mark quickly, but they'll do a good job, but we'll see how we go. But that's just some context on what will happen after you submit. So the earliest anyone can even look at your code will be Tuesday or Wednesday next week. So please be understanding of that. Today we're going to be talking about C++ class types. Now, C++ class types are not part of your assignment in terms of you can do your assignment without understanding these things, which is good. But it's still a really important topic for the rest of the course. Peng and Sam say, is it just pushing it to master? Yeah, we just basically take your latest master. That's what we do. We do we kind of submit it for you. So yeah, just you log into GitLab, you look at your repo, is what's there what you want it to be, and yes, then we mark it. Please make sure you push to Git. None of you watching this lecture will probably make this mistake, but every term there's always 1 or 2 students who don't push anything to the internet and they get 0 for an assignment. So yeah, don't be one of those people. That's the point. Class types. Let's loiter less. Okay, so today in this lecture we're going to be going around a couple of things. We're going to be talking about the rules that surround scope, and we're going to talk about how class and object types are fundamental to understanding how your C++ code works. Now, this C++, as you know from assignment 1, does not really require you to write your own classes like a language like Java might. But everything you've been working with so far in C++ is an object of a class type. Every string, unordered set, stl container, other things, not everything, but a ton of stuff actually relies on classes. So we will, I don't know why switch is there. Sorry, maybe I left that. So we'll be talking mainly about scope and class types today. Now, the first thing we want to talk about is scope, and scope's kind of relevant because until we really look at class types, you can't actually learn a ton about scope, because uh, classes are a pretty essential part of scope, so it's really useful to understand them. And this is also where we're going to touch on namespaces slightly. So, first thing, you all probably are familiar with the word scope in terms of like, oh, a variable has a scope, and if you try and use it outside of that scope, you can't use it. Or, you might know about a global scope or something. But, let's get a bit more formal. So when you declare a variable or any kind of named type, maybe a lambda, a object like a string, a primitive type like an int, the scope of that variable, right, is usually from the moment that it is defined, that's where it starts, and then typically the simplest rule is that it exists until the very next close brace in your code. And this generally applies pretty well for like functions, if statements, while statements, for statements, anonymous braces, and all of this kind of stuff. And there's a couple of key points to this. One is that where this differs from C is that we encourage you to therefore define your variables as close to first usage as possible, as opposed to a kind of C style approach where you meant to declare everything up the top and then initialize them later or something like that. So everything you end up initializing, always declare it at the top. And the reason for that is because we don't want things to have a scope longer than they're needed for, right? Like a particular name. When I say name, I'm referring to a variable. The reason I use the word variable as name is just because, I equals 1 here, you're declaring a variable I is equal to 1, but it's actually like the name means something, right? Like when you try and print that, you're actually trying to look up a name, and the name is I, or the variable name. So we like to declare things close to where we define it because it stops us having things in scope that don't need to be, right? It keeps the program a little bit tighter. And I think that's the main stuff about scope. We'll look at this example. I don't think there's any kind of other key things. Is it possible to give a scope a name? That's a great question. That's actually what a namespace is, funnily enough. So let's have a look at a couple of things here. Just zoom in slightly. So when we pull up our build, did I forget to select a kit? No, I selected a kit. Lectures, lecture 3, scope. Great. So let's look at this piece of code together. Now, you might not have thought about this too much, but this I here doesn't actually, this exists in many different places. And I think another key rule of scope that I didn't include on the slides is that, how when we kind of teach you that you can't use a variable name twice, like we're like, oh, well, you've used it, so you can't use it. And sometimes you get like a redefinition error or, already used or something. It's actually more complicated than that because the rules formally are often that you can't use the same variable name in the same scope, but you can use the same variable name in a different scope. So if we actually look at this program here, and this might be one I can't compile with our CMake because it's a bit of a, those programs I try and show you all that are a bit like, yeah. So like the warnings integrated into our compiler for this course with Clang are just a little bit like, this is a dumb program. So I'm just going to compile this one straight with G++, because I'm just trying to demonstrate the behavior. Demo 301. So this is what this program prints out if we try and do just a standard print. And you'll see that we have a few standard outs here. We have the first one, we have the second one, and in fact maybe I will just quickly name them as well. So we have our 1 here, our 2 here. I know you can all kind of visually count, but let's just do this. Yep, and then we'll compile and run it again. And sorry. So there you go. So these are the 5 instances that we're printing out. And you can see that this first one prints out I is 1, the next one is I is 2, the next one I is 3, what I is on the 4th, and then the 5th instance. Now what you'll notice about this is that we actually have 3 different definitions of I here. We have an I in the global scope. We have an I inside of just a particular like subscope in our function. And then we have another one here. And in all of these cases, you'll notice that they're all kind of inside different braces, in the sense that like if we tried to declare I up here, I equals 4, we would get a compile error, right? Because it's in the same scope. Redefinition of int I. But in the other scopes, it's actually separate. So a name is valid in a particular, is based on a name and a scope product. So you can have the same name in a different scope. Firesyn says if I declared a variable I in the main, that is a different scope than a global, right? Yeah, so there's actually another place we could even declare the I, which would be here. And generally, what really makes the difference with a lot of this is braces. That's a very fast and loose rule. It might be a bit more complicated than that. But essentially, every time there's an open brace, it's typically a new chance for you to scope something. And every time there's a closed brace, pretty much everything that was defined since that open brace is automatically like freed off the stack, essentially. And then Charlie's asked here, we can use braces without loops. Yeah, you can actually. If you just randomly put braces in your code, you're essentially just making a new scope. And if I commented out these braces, it wouldn't compile, because now this I here is actually trying to be redefined in this. It's kind of, think of it like an unnamed namespace or something like that. But that's kind of not super useful. I haven't really found many instances for that to be particularly useful. But the point is, pretty much every time there's an open brace, there's going to be a new scope that ends at the closed brace, and you can redefine the same name there. That's often why it's a bit more subtle than that, and in fact that's also why you see things like if you ever do a for loop where you're like, for int I equals 0, that's why that I can't be accessed after the closed brace. Is it bad style for us to put braces for scope? I mean, I don't know if it's bad style. I would more probably just question what value it would bring you. If there was a reason for it, it'd be fine. But yeah, like what value would it bring you? So that's some really basic stuff on scope. Talked about that for a while. What different ways can we create scopes? Well, we've talked about some. Functions, global scope, random braces. The two that we haven't talked about much that you might have seen though is class scope and namespace scope. So class scope's a big part of what we will be talking about in this lecture, and namespace scope we'll talk about a little bit sometime in it. But most of what this lecture is about object lifetimes and what objects even are. So firstly, in C++, essentially everything is an object. Like even primitive types and other stuff, you can kind of treat them like objects. So we try and treat everything like an object. And formally speaking, an object is a piece of memory, right, that has a specific type, and that specific type might be an int, it might be a string, it might be an unordered set, and that specific type holds some data, right? So anytime you declare a variable that's equal to some kind of data type, it is an object. And unlike certain languages, this has a very low overhead. So some other languages, I don't know, like Java, have a little bit of runtime polymorphism and some other things that can cause their wrapping ints and objects to have overhead. In Java you have an int and an integer type, and one of them's an object and one of them's a primitive type. But everything in C++ is essentially an object. So object lifetime is this notion of scope, essentially, right? Like there's the start of an object scope and the end of an object scope, or a name or a variable, and the lifetime is all the stuff that happens in between it. An object lifetimes start when it comes into scope, and it ends when it goes out of scope. Now, one thing we've kind of glossed over till this point is the idea that all objects in C++ have some notion of construction and destruction. So from classes that you have constructors and destructors, essentially something that's called when you create an object of a certain class type, and a destructor is a function that's called when you get rid of a certain object of a certain class type. But all of this is actually happening in C++ for you all the time. Like when an int comes into life throughout its lifetime, it actually gets constructed at the start in a lot of instances and then destroyed at the end. Sometimes that's just taking it off the stack. Sometimes a basic construction for a string might be that you default construct it to be an empty string. Plenty of things like that. So, and Gert says, are objects automatically freed at the end of their scope? So, sort of. Yes is the short answer. Some objects would be automatically freed on the stack as just part of how these C-based languages work. So for instance, when you define an integer, it would get maybe default constructed in some contexts, and then when it goes out of scope, it simply disappears off the stack. Whereas then there are other types like a vector or a linked list type, which is probably mallocing some stuff, which is probably actually doing some explicit heap memory allocation. And that would actually have to have a destructor defined by the class to free it at the end, right? So construction's a big topic in C++, and it's like pretty much everything in C++ just has a little more like info around it. So here's a whole bunch of ways that we can construct things, and in particular in this example here, we've picked a standard vector to show you the different ways we can construct it. So the first thing is, if you ever just define a type like this, you just say, standard vector int v11 like this, what that will do is that will call the default zero argument constructor, right? So essentially there's a constructor that has no parameters. If you define a type, or if there's a type that expects more than zero parameters, this will fail to compile because it won't be able to match it. And you might think, well, how do I know this? Well, you can have a look at all the different constructors that a vector has. There's all these different methods of construction. And in fact here, you go down to constructor, then it'll show you. So you have a vector with no arguments, a vector with no arguments here, lots of vectors with no arguments, and then it just kind of ripples on from that. So these are all the different ways that you can construct a vector. It's quite a dynamic list of things. Now, we then have our kind of more modern way that we like to create variables in C++, which is your auto name equals type. However, with this one, let me first try and compile this just to make sure we know it's working. However, if we try and just do this without the braces, I think it won't work. Yeah, so when you try and just construct it this way without any braces, it will kind of chuck a tantrum and is like, that doesn't make any sense. And that kind of makes sense why it doesn't make sense, because you're saying that this particular name is this type, right? Because this is just a type here. It's not a value, because a constructor returns as a value. So we have two ways that we could default construct a particular object, right? And that is either using the braces or using parentheses. Now both of those methods are totally valid, and we're going to keep chatting about this, but essentially in a large sense, when it comes to construction for classes, you can pretty much treat braces and parentheses largely the same. In terms of if you use braces, it will just treat it like it's parentheses under quite a lot of conditions. So these are both two default constructed zero parameter vectors, braces or parentheses. We generally prefer parentheses, which we'll keep chatting about. We then have a couple of other types of construction, and both of these you can actually see inside the CPP reference. So if I go back here, you'll see that, oops, sorry. Why does it do that? That's really weird. I think I've noticed I'm alt tabbing. I think the Edge browser alt tabs, which is really strange. So what's happening here is that we're creating a vector and we're actually giving it the begin and the end pointer of another vector. So what this one is, and we can see this, right? If we look through all these different definitions, we'll probably see one down here, which is which is that you can construct a vector by giving it an input iterator to the first element and an input iterator to the last element. So in this one, we're actually using the STL kind of framework to create a new data structure that's being given an iterator of another data structure, which just happens to be a vector. So that's actually how we would, that's one way we could copy items from one vector to another vector, or more specifically, often a non-vector to a vector. We also have this other way we can construct, which is creating a copy. We're going to come back to copies a lot more next week, where the argument we give a vector when we construct it is actually another vector itself. And you can see there's a definition for this one too, where a vector can take in a const vector reference to another vector, like this. So there's tons of different construction methods here. And my point is that all these braces, you can treat them like parentheses, like this. So generally we prefer using braces when it comes to constructing types. We then have the last two very interesting ones, which are initializer lists and this function call here. So there's this notion of initializer list, which it comes up a bit, where when you construct certain types, there are certain types in C++ that have this particular constructor here. And what it does is it takes in a parameter that is just a standard initializer list of a certain type. And what an initializer list is, like, I don't even know how you would define it formally, but it's basically a list of data, right? It's kind of like a, just, you know, primitive array or like a Python list. It's just some kind of collection of data that's typically wrapped in braces. And what these data structures are able to do is to take that data structure and then just kind of populate it, like knock them all in. So in this one here, we're basically saying, I want to create a vector given these numbers, and you just give it a list of numbers. So this is like a really quick way to create a vector. Richard says, by constructing types, do you mean there is something to be put in the braces? Well, by constructing types, I essentially mean if you want to create a new object of a class type, then essentially you're going to put braces next to it. There is one really interesting example, though, that really drives home the point between braces and parentheses, and that is when we're trying to use some kind of construction that involves multiple numbers that might be mistaken for this. So what's really interesting is that this is me trying to create a vector with the number 5 and the number 2 in it. So it's a vector with 2 items in it at the end. Whereas what this one here is this one's actually me trying to call where is it? This one. It's actually me trying to call this particular constructor. And what this constructor does, right, if we have a look here, number 3, we can go down, and it says 3 constructs the container with count copies of elements value. So the two key things it takes here are count and value. So what it says is I will create x of y. So when we go back to our code here, this one is saying I will create a vector with 5 2's in it. So this one is really equivalent to like if you just did like 2 2 2 2 2 as an initializer list like this. So one of the reasons we do like to use these braces as well is because braces pretty much work in all circumstances, whereas parentheses don't work with initializer lists. And also, it kind of makes this a little bit clearer that you're actually explicitly calling a function. But again, we'll keep talking about initializer lists, because the braces, sorry, because there's more examples where you'll be like, oh, okay, that makes sense. Kai says, if there's 3 or above numbers, then the parentheses won't work, right? Well, based on this definition, probably not, because I don't think there's anything that takes in 3 numeric-looking things. But different data structures are the same. So quite a lot of interesting nuance there with the different types of construction that can happen. This was really easy because this was a class type, right? And most of you can kind of picture a vector being a class, and then it has to be constructed, and there's multiple constructors, which hopefully you've seen before. But a more interesting one is for basic types. So C++ is super kind of interesting on the basic types, where this is 3 different ways to default construct a number. Now I'm going to uncomment this one so it compiles, because this won't compile otherwise. But have a look at these 3 different types of construction. So the first one is your C-style construction with an int. Now, general practice is that you should never declare an int without initializing it, because otherwise it's pointing to potentially like unknown memory, like uninitialized values. whatever was left there in memory before. So that is an uninitialized definition of an int, right? If you want the int to default construct, i.e. set it to 0, because an integer type, when constructed, will set a default value of 0, you can do something like this, where you're actually treating the int like it's a class. You're basically treating it like it's an object, just like a vector, just like everything else. You can also do this thing, right? If I replace this with standard vector of ints, it would look really similar to what we had before. Right? That's what we did on the last slide, except this time it's just ints. And you can also construct it to be a certain number, or you could also construct it to be a certain number like this. So this here is kind of generally, you know, another way you could write the equivalent of int n equals 5, or something like that. Now, do we have a preferred way of doing that kind of stuff? Not really. I mean, ints are ints, they're pretty simple. It's more just trying to demonstrate the fact that ints are objects as well. As you can see here, we're essentially default constructing them and doing a few other things. Not obvious. Okay, so we have some other things here. Int n43 equals f, the return of f. Not obvious, you know it. Not obvious, you know that f is not an int, but the compiler lets it through anyway. Then we have this one here, where we say n41 equals the int of that. So what's happening here, and we kind of chatted about this a little bit, is this is an implicit conversion, right? Whereas this here is not an implicit conversion. This is one of the reasons why we try and do the auto on the left for everything. Because if you force the auto on the left of everything, then when it comes to object construction, you don't do any implicit assigning. Because essentially the kind of quirky thing about a C++ compiler is that when it tries and resolve the value of calling f, this will be a double. But then when we assign the value of a double to this int, it will try and implicitly convert it. It'll floor it for us, right? That's just like C-style behavior. But in this case here, because we're explicitly trying to construct an int with a double, the actual constructor of the int will throw an error here. So I think if I try and run this, and I'll get rid of that. Oopsie. Build demo 303. Oh, we got some unused variables. Great. I'm not sure. Let's just try G++. There's a lot of things I'm doing here that we just don't want you to do ever. Yeah, so you can see here that it says warning, narrowing conversion of f from double to int. So this is actually the constructor of the int throwing the error, right? So that's kind of you're shifting the responsibility a bit to something that's a little bit more, you know, kind of clear. And if you really needed to do that, you would do something like this. You would static cast it. Now, static casting it in this case is going to be the same one as this. It's just that it's just clearer what's happening. So I think these three examples are really good to kind of contrast the different ways you could tackle some of these things. Because, yeah, basic types are a little bit more subtle than like our object types. Now, why are object lifetimes useful? Why do we care about object lifetimes? The short answer is because when you can rely on object lifetimes, you don't really have to worry about freeing stuff and closing stuff as much as before. Because typically, right, when you are doing something like mallocing or freeing or opening a file or closing a file, the problem is that they're often just kind of stored in variables, and you often forget to finish something up. Now, if again, the first time any of you would have done some object-oriented programming, you know that the cool thing is that you can essentially bake into the class itself a set of instructions to follow when the object itself is deleted or it goes out of scope, right? So, and you've probably done this, and we're going to do more of this in C++, where it's like, you could have an object, like a vector, where what happens with the vector is this vector might malloc something, right? Or like, let's say this one here, this might malloc something. I don't know the implementation of a vector, but let's just pretend it probably has to malloc something because it's a dynamically sized array, right? So the vector itself is probably using malloc under the hood to create memory. And we don't want to use malloc at this point in the course, so please don't use it. There's no need to use it. It might malloc something, but it doesn't free it, right? We don't call v2.free. If this was a COMP 1511 course, we'd have to say like standard vector int free or some random thing like this to actually free it. But what's happening here is that when we define v2, v2 goes out of scope right here, and therefore the destructors of v2 and v3 are called. And as part of the destructor, it frees it for us. So that's why object lifetimes are really useful, because we can rely on them to say, once this object goes out of scope, call the destructor and handle all the messy stuff for us. And in fact, that's why things like this are also useful, because if you open a file as part of an input file stream, you can do stuff with it. And if you didn't have this f dot close here, then it probably wouldn't matter, I don't think, in this case, because or it would. I mean, I think it'd be fine. Just rereading it. Yeah, this one would be fine. So it's like, the point is, because the name was defined inside that function scope, once the function ends, it would free or unallocate or do whatever any of the underlying resources here. So I'm not familiar with input file streams too much, but I'm pretty sure in this case, if an input file stream that opened a file goes out of scope, as part of its destructor, it closes the file for us. So this is really good from a programmer's perspective, because library writers are probably much better at making sure that things clean up after themselves properly than novice programmers like all of us. So George has a great thing here, which is that, so for most types, C++ has automatic garbage collection. So I don't know what the official definition is, but what I would probably explain is that in a language like C, everything you put onto the stack is automatically taken off the stack and deleted as it goes out of scope, right? In C also, whenever you malloc something, it stays there until you free it. Those two principles are still true in C++. The difference is that because C++ has objects, because it has classes, we can essentially have an object that acquires a resource, manage it on the stack, and when that object is taken off the stack, an instruction is sent to free it for us. So it's kind of like these things manage themselves. So I wouldn't say so much that C++ has automatic garbage collection. It's more that the nature of having objects in C++ allows library writers to manage their resources really efficiently, and without issue. We're going to touch very briefly on namespaces, because I don't want to spend a lot of time here. You've kind of seen these in your assignment. Namespaces are essentially ways where you can just scope things arbitrarily. You can just add arbitrary scopes to things. We've kind of got these examples here where, and I'll just dump this in quickly. If you had something like this, where you were like, here's a namespace, and then here's a namespace, or I created like a variable here called int I, then essentially what happens is that if I want to print that I, if I want to do that, I can't just do this. Right, this won't work. If I try and do it, it should break. Yeah, it's like, I don't know what I is, and there's no IO stream. Yep, it's like use of undeclared identifier I, because this is actually in the COMP6771 word ladder scope like this. So those two colons we actually use are essentially just referring to scope. So this will work now because I is not a name by itself. It's not a global variable. This is actually a variable inside of the namespace word ladder scope inside of the COMP6771 namespace scope. So the reason we use namespaces is so that we don't have to complicate variable names. So like if you want to create your own vector, right? If we want to create a C++ vector for ourselves, we could just make a vector here. And then if you want to use it, we would never get this confused with the STL vector, because we wouldn't be using the STL vector, we'd be using the 6771 vector. So it's really a great way to try and organize types. And yeah, so std is a namespace. So in every single one of your libraries, like when you hash include, like if you were to look at what vector.h looks like, it would look something like this. It would be like namespace std, and then it would say like class vector. So the actual class itself is defined inside the std namespace. And that's why, like, for your word ladder, it's in, like, it's COMP6771 colon word ladder or something like that. Namespaces can be declared anywhere. I'm pretty sure they can be declared literally anywhere. Like, you could just say, like, namespace Hayden here, and then say, like, j equals 6, auto j equals 6, and then here you would have to say Hayden j, like that. No, you can't, maybe. Namespaces can only be defined in global or namespace scope. Oh, yeah, of course. Sorry. I was getting that mixed up with functions for some reason. Like, you can do functions anywhere. So, essentially, namespaces in the global scope or in their own scope, so that you can nest namespaces as much as you want. This makes sense because otherwise your code would be unnecessarily unruly and just all over the place. But so no, they can't be declared inside functions. I was thinking about the functions for some reason. My brain got messed up. Void says, can you touch on the using keyword? So in C++, you might have something like this, where you go, okay, we're going to compile that, and then we'll run. Oops. Yeah, when you run it, it'll run fine. It compiles. It's a simple program. But there's a bunch of people that are kind of sick of scoping everything, so they do something like this. They say either, like, the worst thing you can do is using namespace Hayden. And then they'll do something like this. Now, what using namespace Hayden does is, the easiest way to explain it is that it takes everything in the namespace Hayden and it puts it in the global scope. Because in C++, if something is defined globally, right, like out here, you can just access it, right? You can just access it anytime. I can just build, I can run, and this will work, and I don't know what the... Yeah, I could run it, it would print out 5, right? What do we got? 302. Prints out 5. But if I try and say using namespace Hayden now, the problem here is that we're polluting the namespace, right? And what's happening here is now it's going to say reference to J is ambiguous. So the compiler's literally like, hey, this is kind of confusing. Now, often the compiler will pick up on this for you, sure, but like from a readability standpoint, this makes it harder because now suddenly something that is in a particular scope is no longer like clear what's happening with it. So that's kind of why we won't ever use using namespace something, because all this does is takes everything in the namespace Hayden, brings it into the global scope so that I can use it as if everything in here was just magically already defined globally. Now, some people get around that by saying, oh, instead of using this, I'll actually just do this. Right, this is a shorthand. I think this is how you do it. I never really do this. Yep. This is like a shorthand way of saying that just to avoid having to write Hayden : J all the time, right, I would just say using Hayden J. So just in particular the J. That's it. Not everything, right? Not everything else in the namespace. And some people do this by saying things like, using standard vector. So that you don't take everything in the std namespace and bring it in, but you're just bringing the vector in. This is marginally better, though. For the sake of simplicity in this course, we just still say it's bad because it just does create more ambiguity. In the real world, you're probably more likely to use that sometimes. I don't think using namespace something is ever a good idea, though, because namespaces are often quite large. That's all these slides really get to. Chris wrote these ones, so typically they're extremely detailed, which is excellent. So you can go read through them in your own time. I think the only other note I wanted to make is that I think there's some anonymous namespaces, but I don't remember where it was. Maybe I got rid of them. I might have got rid of them because I'm like, that made no sense. Anyway, that's kind of the quick thing on namespaces, right? This whole lecture is not about namespaces. What this lecture is about object-oriented programming, or classes and stuff. So fairly straightforward principles of object-oriented programming. Why do we have classes? We have classes because they allow us to abstract complicated pieces of code, and they allow us to write a nice clean interface like vector, which is a very complex, dynamically sized, templated data structure with a really friendly interface where you can how do I go back? Has all these really friendly things like push back and front and back and begin and end and size and blah blah. Um, Ooh, that's a really handy function. I never saw that one. Shrink to fit. Oh, there you go. We were talking about that last week, weren't we? About does it reduce the size? And I said no, because that's just useless time. But it looks like you can call it explicitly. Some of you probably already saw that. That's very cool. Yeah, so we like it because it's a nice abstraction, right? It helps us separate the interface, which is what you read on CPP reference, from the implementation, which is what the people who wrote the library actually had to do, which is a lot more complicated. So we like that. Now, with C++ classes, we're not going to get too much into the whole, what is a private or public thing, because we assume that you know it, and if you don't, it was a prereq? I can't remember. It's very confuses me how some of that stuff happens. But essentially a class is a new type. It's like an int, it's like a double, it's just a type. We create it using keywords class or struct. Typically classes are made up of, at the most basic level, variables or data and functions or methods. So it's a collection of functions and data. And there needs to be at least one private or public section, right? A class can't be like totally empty. And so I mentioned that classes are made up of functions and member functions and data members is what we call them in this course. But class functions, object functions, members, member functions, data members, fields. Like there's a whole bunch of different names for it. But essentially all you typically will define member functions and data members inside the class itself. And you can define them in the class or you can define them outside of the class, but still in the scope. So we're going to have a look at a really simple example here, and we're going to build out our knowledge of classes slowly. I don't think I had this as an example. Okay, so here is a really simple class in C++. Now, what you'll notice about this, firstly, is that it looks pretty similar to what you would do in a language like Java or something. Probably a couple of the key differences to point out are that one, in C++, from my memory, I haven't written Java in like 4 years now. So one is that you can declare things in C++ without implementing them yet, right? So this is a function. This is a private function that is being declared. We haven't defined it. We haven't actually explained what it does yet, but we have declared it. So you can declare things without implementing them in terms of functions. The other thing is that in languages like Java or possibly even C, I don't know what C Sharp's like, but typically you put public, protected, or private in front of each declaration or definition. So if you have like a field or 3 fields or like 5 functions, you'll put like, private void, private member function, private int, private data member, like that. Whereas in C++, we actually just use these public colon things. And essentially when you write public, protected, or private like this with a colon at the end, it will apply this particular privacy setting to everything underneath it until it either reaches the end of the class definition or until it reaches another kind of privacy keyword. So in this case, it's saying, okay, everything here is public, everything here is protected, everything here is private, and you can do it multiple times. You can define public multiple times. Generally speaking, you don't, though. And very little in this course will you ever do protected stuff. So for the short term, it's pretty much public at the top, private at the bottom. And we like to keep public at the top because that's what people read when they're reading the file, right? It's like it's a data type. Like if you haven't actually written a web page for it, they're going to have to look at your .h file. And in particular, I think something I've kind of glossed over here is that I called this blah.cpp just because I wanted the syntax highlighting. But in reality, all of these class definitions are in .h files. So this is like a class definition. This actually would be in a .h file, so that's where you would find something like that, not in a .cpp file. I don't really know what the convention is with Java, but generally you'd put public at the top because someone would actually be like reading it. Now let's have a really basic look at an example of class usage. So here I've defined a class. It's called myClass. And it's got 2 sections. It's got a public section and it's got a private section. A couple of things that you'll notice here are that in the private section I've got an integer called I, and all of my class fields, my class variables, that is, they're not quite global and they're not quite local function scope, These are kind of like global to the class. I can use them in any of my class functions. I put an underscore at the end of it because in all of our class scope data members, I put the underscore so that we can understand that it's a class, that it's a data member of a class, and not mistake it for like a local function variable. And it kind of saves us needing to use the this operator because the this or the self operator kind of just takes up a lot of space. So we put this underscore at the end. The other thing that's kind of clear here is we have a public function called getVal that returns an int. And it returns the I, so this is basic encapsulation, and then we have a constructor here that takes in an int, and it sets the private data member I underscore to be equal to the value of that int, so it sets it to be equal to I. So fairly basic class. And then underneath here we have our main function, which all it does is creates a variable called MC, which is equal to class type myClass. And we construct it by using the braces because we try and use braces to construct everything unless we really need the parentheses. And we give it a 1. So this is essentially saying create an object on the stack called myClass, and we're going to give it an argument of 1 when we pass it in, and then that will create a new object of that class type. And then on the next line we can standard C out the myClass.getVal. So myClass.getVal will call the public function, and we can only call public things. If you try and access something that's private, C++ won't allow it. So if I say mc.I underscore, what will happen here? It's going to complain. It's going to say, sorry, that's a private something. I underscore is a private member of my class. Brr. So that won't work. So you can only access the public things like that. So fairly straightforward usage of classes. There's maybe some slight syntax differences, but generally pretty much the same. Some of you who are familiar with the this pointer might be wondering why we're not using that. So similar to other languages, we have this notion of this, where we can, is that in this one? No, it's not. Instead of saying this, we could use this. So this is a pointer to the actual object inside the, so if a function uses the this pointer, then the this refers to a pointer to the object that called that function. So in this case, MC is the object that called the getVal function. So this is a pointer to MC, and therefore we dereference it and we get the class member that it's relevant there. It can't be null, I think, by the very nature of what it is. So I don't think there's much dereferencing risk there. But basically we just don't use it because the underscore is like this pointer. The main benefit of it is that you're able to more clearly distinguish variables that are just exist in the function from variables that are based on the class. So that's why we use the underscore as a convention, to essentially avoid us having to litter our code with the this statement. Okay, now, where things get a bit more interesting when we're defining creative classes is that we don't always write all of the class in a .h file. So far I've said that the class definitions we have are written in a .h file, like this one here. Now, naturally this one wasn't, it was written in a CPP file, but what you would typically do here is you would create a .h file called basic.h, and you would put this in here, call this basic.h, and then that's how you would use it. You would compile it like that. So when I do 304, I feel like this won't compile. Oh, it did. That's kind of what you do. Though in reality, you will tend to actually break these up, right? All of the information about what your class is and how it works is not always captured inside of your immediate class block. And in this program here, sorry, I think I might have forgot to update this specific example because I changed this to simplify it. So let me just update this really quick. Cool. Just make a note of that, sorry. I changed some things around to simplify some things this term. So what you have here is a class called person, and it has 3 functions here. The first one's a constructor. You can tell it's a constructor because its name is the same as the class. And that constructor takes in a reference to a const standard string. It takes in an integer age, and then we have two functions here. We're using the new function syntax just for fun, called getName and getAge, and both of these return they don't take in anything, and they return a reference to a const string and a reference to a const int, respectively. And there's our private data members with the underscores under them. Now what you notice here is that these three functions are declared here, but they're not defined. I could define them in this class like we did back in basic 304 before I pulled this out. Right, we could do this where we create the constructor and we define it right there. We declare the constructor and we define it right there. Or alternatively, we can just declare it here and define it somewhere else. So defining it somewhere else, I can just do below the class in this case, frankly. One sec. And I can do that by writing it just like I would in the class, except the one difference is because I'm doing it outside of the class, I need to scope it with the name of the class. So if you notice, this would be exactly what the definition would be if I had this inside the class. It would just be that, right? So when it's outside of the class, everything's the same, except I have to scope the actual function name or the constructor name or the destructor name or anything really with the class here. So that's why it's person : person. And then I can actually implement it. So it's declared in the class and then it's implemented here. And I've got my, reference to const string, my reference to const int. I specify what happens, name and age, get assigned to name and age here. We don't have to scope these variables. We don't have to do anything with this because this whole function is defined inside the scope of person class. So everything inside of it kind of assumes as if it's being like it's inside the class, right? So we don't need to do anything more than that. And then for the other functions, getName and getAge, we can just write those as if we were doing it too, right? So we just have our scope here. The scope's on the name. Doesn't have to be at the start of the line. The return type's at the start of the line. It's just on the name. And this makes sense because without that, all that's going to happen here is that C++ will think it's just another global function, just like all the other functions you write. And then it's going to not compile because it's going to be like, what the hell is name? I've never seen that before. It's not in my scope. It's not in the function scope. It's not in the global scope. And it's just going to be like, no. Whereas here, now that it knows that I'm actually defining the getName name inside the person scope, it's like, oh, it's this one inside the class person scope. Kai says, why is age const outside but const inside the class? That's just a typo. That's fine there. Yeah, that's just a small typo. Yep. Cool. And then we can use it the same, like we create a person. This is another way of doing it. I'm just showing you some different examples. Generally, we prefer this way. Auto p equals person Hayden 99. That's how you should do it. But you will see lots of code written like this. So auto on the left, we use braces to pass in the parameters. And then this code should compile and run totally fine. So that's 305, right? Yep. Cool. Now, one of the only kind of like relevant distinctions here is that typically with C++, how you would do this is that you would take your person class, you would put that in another file called person.h because your class declaration and some of the definitions go in the .h file. We'd have to include standard string here, right? You take your class definitions that didn't make it in, like these, and you put those in a library file, which I might just call, I don't know why I called it. What did I call the other one? Basic.h? What stupid name did I give it? No, it wasn't basic. Oh, person.h. Oh, it was called person. Sorry, I thought it was a different name. Sorry. We create one called person.cpp, and then just like your old C files, you have your .h file, you have your library file that you compile with, and you have your main function that actually runs it. And then if we wanted to run all those together, we'd have to update our CMake lists because we would have a C++ library that I've defined, which is my person.cpp. So I would have to do something like that. And then because my main function includes the .h, but it also relies on this other CPP file, I have to link my other CPP file. So now we're compiling two CPP files with a common header into the same executable. And if I reload the window here, because I've updated the CMake list, we should be able to build this one successfully now. But I will need to hash include the headers. So I need to hash include person.h, and I'll need to hash include string as well. And I'll probably need to do the same thing here. Oh, no, I can just include hash include person.h, right? So this is fairly standard stuff that you would have done in other courses, from what I've been told. And oh my god, it worked. And yeah, and then this should just work now. So if I just do 305, it says Hayden. It does what I asked it to. And that's kind of a standard thing you would deal with. Firesit says, do I need to hash include string if person.h already includes it? Yes, because how do you know person.h includes it? You know, like you might not. So you're making your code less robust here, because person.h might not have that, might have it, it doesn't really matter. Generally, it's like if you use a particular library in your code, then you hash include it there. The compiler will handle the duplicate imports for you, but it makes sure it just generally is considered a, you know, better readable code. Cool. And then I think just the obvious question that comes from this is, why would you do this? Why would you not just include everything in the .h file? Like you could just put it all there. Like nothing forced us to put it here. And the reason is because two reasons. One is .h files are also code documentation, right? So it's really good to keep this simple, because it means that someone who's just trying to read what your type does can just read it without seeing all the implementation, right? Because this is still like a C-ish language. And the second reason is because remember that the way that C works, it goes and compiles all of the files separately. So if you have like 5 files all using a vector, and the entire vector implementation is actually defined in the vector, then that's going to be massive compilation times, because every single file that includes the .h is going to have all that copied into it. Whereas like if we just compile with the prototypes and the headers, and then we link it together at the end, it actually speeds up our compilation time. Kai says, do we need the .h? That's a good question. So the reason that I've been including it that way is because an old environment that we had set up required us to do it, because it only looked, if you didn't have a relative path, it only included it from the include folder. Zins, do we need to separate the class in assignment 1? No, there's nothing to do with classes in assignment 1. When you hash include the path, is it always relative? Yeah, I believe it is. It's just that's a relic from a previous environment. I think we've changed it since then. So typically, like if you just did this, it normally only includes it from the include folder. But I think we turned off some checks and things since then, so that's why it's still a habit. Anyway, let's take a 5-minute break, just because it's been an hour, and then we'll come back to it and finish off the rest of classes. So thanks. Okay, welcome back from the break. This has been fun so far. You guys are all so tame tonight. Everyone's so quiet, which is good, because I have to read the chat less, but the questions are good. Keeps me focused. Let's keep going through more about classes. This is a fun little lecture because there's just lots of little things. Next one. In C++, you'll actually see a lot of the time structs written down somewhere. Now, again, you should probably know structs from C, and structs, they're just data members, right? It's just like it's kind of like a class with no functions. But in C++, classes and structs are exactly the same. And what we mean by that is if you go and write struct instead of class or class instead of struct, they will be the same thing. So just be wary of that, because they're not quite as different as you might expect. Now, on top of that, or I guess, you know, given that fact though, there is one tiny difference that's really important to note, and that's that if you create a class where you don't actually give it this like privacy settings, and you create a struct in the class, by default, everything will be private, and in a struct by default everything will be public. But that's the only difference. Everything else is like the same. So that being said, we will generally use classes always in this course. The only times you would really want to use structs are if you're ever defining some kind of object type that only has data members, and you have direct access to those data members. And yeah, you can have structs are exactly the same as classes. So you know they do construction, they do destruction. They have lifetimes. They get put on the stack. They can have functions. They can have data members. It's all totally the same. It's just the default nature of that, and the meaning itself, right? Like using a struct when you should be using a class would naturally confuse someone. So that's why we want to be careful with it. So I kind of touched on this already. 5.8. Sorry, I'm just making some notes for myself. Where anything that's declared inside the class needs to be accessed through the scope of the class. So we did this in the previous example where we created a class like foo, but then when we wanted to actually go and define some of these three functions that we declared, we had to scope everything with foo colon. So this is standard. Pretty much anytime you do something outside of the class, you need to give it the appropriate scope so that the compiler knows what you're referring to. Because foo doesn't mean anything as a function. It only means something as a global function. It only means something in the context of a class. Now, in C as well, in C++, you also know that you can sometimes declare incomplete types. Incomplete types are where you essentially use a type that, how would you say it? An incomplete type, it's where you use a type that the compiler does not yet know really what it is. And an example of doing this is if you try to do something like this, the compiler would not know what it means, because it actually evaluates the elements of the struct prior to how would you put it? It writes the elements of the struct prior to actually resolving the name here. So like it looks at this before it actually gives the struct a name and a meaning. So in this case, it'd be like, what the hell's node? Whereas you can kind of do this. And what I said before was pretty much a gross oversimplification. The main point here is not so much the compiler timing, it's more just around how does that even make sense for a node to consist of a node, right? That's kind of why we use pointers in structs a lot of the time. But Kai says, I don't think that's C compatible. Yeah, so I mean, C would still compile with C++, but not the other way around. This slide you don't need to worry too much about. It's more just like here's an important fact about it. What we're going to do though now is we're going to get into constructors in more detail. In the sense back here, we talked about constructors in the, where is it? We talked about constructor here, but this was like how to use a constructor and define it. Like what do you do? Now we're going to talk a little bit more about how it works, because constructors are a little bit non-trivial in C++. The job of a constructor is to set up an object, right? So you create an object of a certain class type, and a constructor sets it up ready for use. The way a constructor works, though, is that it goes through three distinct methods of setup, and two of them you should be already kind of aware of, and the third one we're going to talk about. So, firstly, a constructor tries to initialize data members via an initialize list. Then it tries to use let me take a step back. I've probably stepped over myself here. Firstly, a constructor will try and use an initialize list, which we're about to talk about. Then if it's a built-in type, it will just leave it. And if it's a non-primitive type, like a string or something, it will default construct that string, and then it will execute the function body. Right, so that's kind of the flow that constructors work with. And as an example here, we're going to talk firstly about initializer lists, and then we're going to talk about the flow of things. So we have this little sample piece of code here called my class. It's exactly the same as it was before. The difference is you'll notice that unlike the previous example where we did this, where we took in the I as a parameter and then we set the I underscore to be equal to I, what we did this time was we had this little colon followed by the I underscore and then braces I. So we've actually got nothing in the constructed body anymore. It's all in the initializer list. So this, what I've highlighted here, is what you call, think that you call it uniform initialization, but it's an initializer list used in the construction. And this particular phase occurs before the body of the constructor is called. So if we have a more complicated class, like let's open demo 306, if we have a more complicated class with, say, like an int j, a couple of things have to happen here. The first one is if we want to use uniform initialization, or default initializer list, I can't remember what it's called, god damn it, then you actually have to put these here after the colon in the same order that they're declared in the class. So if I want to initialize the I parameter that I'm given in when someone constructs into the I underscore variable, I do it like this. I say that the I underscore variable is going to be constructed as this. And then if I want to do it for j, I do a similar thing where I say the j underscore class data member is constructed as j, and then I also have to give it another parameter there. Right, that's kind of how I do that. And then this will work. Like I could sum these together. Like let's just say get val's the sum of these two things, and when I construct it, I have to do that. So when I run this and I run 306, then we compile 306, we get 9, right? So it sums those two things together. Now you might be thinking, why don't we just do this? Like, sure, it looks a little bit cleaner, but why do we invent a whole other type of syntax, right? Like, I mean, that seems very extra. Like, why don't we just do this? This worked fine. There was no major problems with it. And the answer to that question is it all comes down to how C++ goes about initializing things. So if we go back to our previous slide, where we had this, so I'm just taking more notes for myself. We have this. Have a look at the order that things happen here. So it does the initializer list for a variable, and then it'll default construct things. What's kind of missing from this slide is that it's not making clear that all of these things happen prior to your actual constructor body being called. That's really important because what that means is, in this case, what happens is like let's say I got rid of this and I put j here. So I said j underscore equals j. Let me trace through for you what happens here. So first thing, it goes through all the initializer list stuff. So it populates the I data member to be the value of I that's passed in, number one. The second thing it does is it goes and default constructs, if applicable, all of the remaining data members that weren't initializer list. So because j I didn't put in my initializer list, it now comes here and it default constructs that. Now in the case of I, because it's a built-in type, like ints and stuff, I'm pretty sure it just leaves it as it is, just like a normal variable declaration. I think I might have said something different in my tute today. I'm sorry if I did. So it actually just leaves that alone, right? That was step 2, is default construct, if applicable, the rest of the data members, and then step 3 is execute the body, right? So having the initializer list doesn't just make your code look a little cleaner. The other kind of improvement it has is that it actually prevents things from being unnecessarily default constructed. So what I mean by that is, let's imagine that int j here was like this class or object with it had a big construction overhead. So to construct it required a lot of memory or processing, like a standard vector, right? Maybe as an example. Let's say we had a standard vector of ints here. And we pass in a standard vector of ints that's like by reference here, const reference. And then we say j equals j, like this. We kind of copy assign it. What happens now is that the I by the initializer list gets initialized. then the J default constructs. So like that means that the entire vector does its whole setup thing. It literally creates the object, like a default construction, like an empty vector. And then the function body gets executed, and then you assign over it. So you've essentially just default constructed a vector, and then you've assigned over the top of it. Whereas if you do something like this, it skips that whole default construction stage, because in the order of things, we actually look at the initializer list before we default construct things. So that's the other benefit of putting it there. And to go back to the previous example, because Firesin had a question, which was like, so I could do like j equals I plus 5. Yeah, I could. And it would be 9, because that's how it works. Is the initializer list popular? Oh, thought I could. Pretty sure I can. Yeah, I can. I just can't write code. Hi, everyone. Okay. No. No. Unused parameter j. Plus j. Write properly. This should work. 14. What? Does that make sense? 5 plus j, which is 4. Oh, yeah, it does. Wait, what? Does it? Oh, yeah, because yeah, it does. Sorry, the math checks out. My brain doesn't check out. Yeah, so that's all good. Great. Really, really interesting stuff. So that's a constructor initializer list. You should always do that when you can. The synthesized default constructor. So what happens with C++ is there are these notions of synthesized methods, which is basically if C++ notices that you aren't doing something manually, it will automatically create one for you. So what I mean by that is that in C++, if you don't create a constructor, it will figure out what to do for you. It'll actually create this like kind of hidden constructor. So if we have a look at an example here, we have this class A, which just has an internet. Now, because there is no constructor defined here, C++ will actually generate a constructor for us. In this case here, because we have a constructor we've defined, C++ will not generate a constructor for us. So then when we have this main function here, we do int I underscore with the braces 0. And this is just a standard object construction of an int. So it actually will set the default value to that. We have int ji, which is just untouched memory, C style. And then we have a here, which will call the default constructor of a, right? Which in this case will still leave a unassigned because it's just a normal variable. But when we call b without any parameters, it will call, in this one it will actually fail to compile, I think, because, like I'll show you this. So I'm just going to override this file we have here. VLab freezes when I try and copy and paste things. Okay. Class A. Should have put this one as a specific example. Hey, okay, great, copy. Oh no, what's the problem? What in the F is happening? Okay, sure. Great, and we're nearly there. Just one more random chunk of code to copy. Nearly. Oh, just so close, I can feel it. So, there we go. So, what's going to happen here, which is a little bit subtle, is that even though we don't define a constructor here, the compiler will synthesize one for us. With this one, because we defined a constructor, check out what happens. So I go to build this, and we get a compile error, and it says, no matching constructor for initialization of B. So what this is basically saying, right, is that I don't know how to construct B with no parameters. The compiler's like, there's no function to do it. You gave me a function for the single parameter, but there's no function for no parameters. But the thing is, that's also true for A. It's just that because we didn't define any constructors for A, the compiler generated one for us, a default one. So the kind of golden rule here is the second that you define a constructor, this is true for other things like destructors, the compiler will not generate one for you if it can, right? So once you define one constructor, you need to kind of be aware that you might need to define them for different use cases, particularly the default case. So that's just something to keep in mind. So the synthesized default constructor will happen whenever you don't like start defining constructors. Another really cool thing is delegating destructors, which is constructors can call other constructors inside the initializer list. This is kind of cool. I can show you this here actually. We can solve this problem. Is if you say, actually, I would like a B that takes in nothing, you can actually call B again with a particular value like this. So it's kind of like instead of going B equals B equals 5. Like instead of doing this, which is what a default constructor is, right? Like we've got a constructor with no parameters and we just set B equal to 5. We can actually go, we can use like the initializer list, but instead of using a data member, we can just use the other constructor and we can just say B's 5 like that. So it kind of bootstraps itself. It calls itself here. And then this will make this compile now, I believe. Or not. Calling a private. Oh, yeah, because everything in classes is private by default. Derp. Really simple. 306. Unused variable I. Who cares? They're going to complain about everything because the compiler is trying to stop us writing bad code. But I used A. Did I not save it in time? Oh, private field's not used. Ugh. What do you want from me? Anyway, you get the point. This will work now. If it wasn't trash, kind of simple code. Oh, I had an example for you. That's great. This is another example if you want to develop your knowledge further. This is pretty much what I just did there, except it works and it's a little bit more elaborate, but it's the same principle. It's 7:30, so I'm not going to spend too much time there. And then we have destructors. So destructors are functions that are called on the object at the end of its lifetime. Basically, oh, God, my head hurts. Basically, when it goes out of scope. Pretty much the only time constructors exist, because they don't really exist that often, if you're freeing pointers, i.e. things you've mallocked, you're closing files or closing network connections or sockets that you've opened, or connections to databases or other things, or if you're unlocking mutexes, like particular shared resources you've got to lock on as part of multi-threaded code. But besides that, you don't really deal with it. And in fact, modern C++ has very little destructors in it because nowadays you can do a lot more on the stack. So generally, like, there's not much really of any reason to use raw pointers anymore, which we're going to talk about more next week. The week after next week. And the only other thing is that we put this no except statement at the end of our destructor declarations and definitions. We're going to talk about what this means at the end of next week, but for now, which I don't think you'll do too much of, anytime you define a class destructor, you put a no except out the end. All no except really says is that no exceptions will be thrown. And this is important because your destructor can't throw exceptions. The terrible things happen. Again, that's next week's topic, but that's the gist of it for now. I don't have anything to show you with this because honestly, without doing file opening and mallocing, you don't really have destructors. So like a destructor for B might be like, oh, whoops, tilde B, like that. That's a destructor, and then you define it there. In today's tut, my tut, which was recorded, or other tuts, or this week's tut, we actually have an example where we use destructors and constructors to keep track of a static variable that tells you how many instances that class exists. That's pretty much one of the only trivial examples we can show you, really, without kind of it being a bit tripe. but we will talk more about where you need destructors later on, I think. Cool. You'll probably, yeah, you'll be writing destructors for your assignment, I think. Oh, I don't know, actually. We used to, maybe not anymore. You don't need destructors unless you are reference counting or dealing with raw pointers, I mean. Yeah, I don't know, probably not. That's why we don't talk about it much. It's generally bad style. What did I do? Okay, yeah, there we go. Okay. A couple of other really important things about constructors is that so crazy. If a constructor has one parameter, just one parameter, right? The compiler will create an implicit type conversion from the parameter to the class. Now, this is a behavior that happens by default, and you have to opt out of it. And what I mean by that is if we have a look at this piece of code here, 310 explicit, jumped ahead a bit, you can see here that if we have this class called age, and the constructor has one parameter, so that's the key thing here, the constructor has one parameter, not 0, not 2, but has one, what'll happen is that you can always construct it like this by saying, age A1 equals 20, or you can construct it like this by saying A2 equals age of 20, right? They're the two standard ways we've talked about, and we prefer this one. But if there's just one parameter, you can actually also do this. This is what we call an implicit construction. And the key thing to understand here is that the right-hand side is not the type, right? So in this case here, auto A2 equals age 20. When the right-hand side of the equation gets assigned to the left-hand side, the right-hand side is as an age type, whereas here the right-hand side is a 20, and it gets converted to this automatically. You can actually do this. When can you do it? I'm trying to think about. I think vectors will let you do it. I think with vectors you can say standard vector int a equals 1, 2, 3. I think you can do that as well because it basically will pick up on that you've passed it a single parameter initializer list, and then it will implicitly construct it. So that's what we call implicit construction. So this code should work here if I do 310. Unused variable A3. Ugh. All right, I'm gonna do it. Let's do it. Demo 310. Okay, so that one works fine. But if I put an explicit out the front of my single parameter constructors, then when I go to compile it, the compiler will complain. It'll say conversion from int to non-scalar type age requested here. So basically the compiler's like, oh, I'm sorry, I don't really know what that is. I don't know how to convert an int to a goddamn age. That doesn't make any sense. And this is actually another reason that we like to put auto on the left. Because what do you notice about this? I can't say this. This doesn't work, right? Like if I'm kind of trying to implicitly construct an age class, this doesn't work because it'll think it's an int. A3 will be an int, not an age. So that's the other reason why we like to use auto on the left, because it forces us to actually construct this on the right-hand side, which will stop us kind of writing all these ugly implicit constructions and stuff like that. So that's just another reason we ask you to do that. This is another example you can look through. It's to do with a vector. Yeah, that one's a little bit more interesting, but again, just for the sake of time, I don't want to get caught on it. Okay, next little bit. Const objects. So I was just thinking about it'd be cool if I cared enough to spend all that time to like annotate my YouTube vids to like, those like YouTube vids now where there's like the bar down the bottom has like the little sections and they have like little titles, so you could be like, oh, const objects, that's where that is in the lectures. That'd be cool. But I don't know if I want to sit down and do that for every lecture. Maybe if I pre-recorded them to reuse them, but anyway, thanks for listening. So we're familiar with const. We're familiar with const variables. That's like what we did in week 1. But one thing we haven't talked much about is const member functions. So const member functions are member functions that are only possible to do on. Oh, sorry. Let me read the slides because it'll probably make more sense. Member functions are by default only be possible. All right. Okay. Let me just articulate this. All the member functions that we've defined so far are what you call non-const member functions. And a non-const member function can be called from a const object and a non-const object. But you can make const member functions that can only be called on const objects. Now I know that sounds like a whole bunch of const, not const, like word magic. So we're actually going to look at an example here which will make it a little bit clearer for you. If we have a look at example 308, you can see for example 308 we have a person class. It has a single parameter constructor that we've marked as explicit, which kind of uses uniform initialization to initialize the member name, which is a string. And then you can see we have a set name function that takes in a name and it sets the name to that, and we have a get name function that returns a string, and which is the actual string stored. And then our main function has an auto const p1 of a person called Hayden, and then it prints out the person's name. Right, so that's a pretty straightforward program. We should be able to build and run that fine. Oops, that's the wrong thing. Sorry. Build 308. Explicit's generally considered good practice because most of the time you want things to be, explicit. It's better for everyone. So I just I don't want to compile it that way. Sorry, I meant to like build lecture 3, demo 308, and then it prints Hayden, right? So this is exactly what we expect it to do. Now, I don't think this slide is going to take me any further, so I'll have to do the rest. Oh, it did? Is that missing stuff? Oh, it is missing something. Okay. This is so weird. There's like one of the slides I haven't changed since last year, so I don't know, maybe I'm crazy, but I'll just show you on this and then we'll copy it in, which is that in our main function we're actually doing two things here, which is we're creating a non-const version of a person called P1, which is Hayden. We're setting the name of that person and then we're printing it out, and then we're creating a const version of that person. Now you're familiar with using const stuff because you've been doing that in your assignments, right? You can create a const object or you can create a non-const object. So here we kind of have these two examples, right? Auto P1 equals person, and then we have here auto const P2, let's make this one P2, equals person as well. Now, the main point that we're trying to make here is that these are what you call member functions, and this one here is what you call a non-const member function, right? Now, a non-const member function, which I think might have been the opposite of what I said before, can be called by a const or non-const thing. So you notice down here, P1 and P2 are both persons, right? They're both persons. It's just that P1 is a non-const person because it's not const. You can modify it, right? You can change P1 to be equal to something else. P2, though, is a const person, which means you can't modify it to be equal to something else. Now, that's really critical because const objects cannot call non-const member functions. How do I tell whether a member function is const or non-const? It's actually really simple. If there is a const written at the end of the parameter list, it's a const member function. That's it. So you can see here that this get name is a const member function, and the set name here is a non-const member function because there's no const written here. If there was a const written here, it would be a non-const member function. Now, what are the properties of a const member function? It can only be called by a const object, and it can't mutate anything inside of its function. So let's first just like look at this. So you can see here that our non-const objects, the person, our modifiable p1, can call both setName and getName, because non-const can call non-const objects can call non-const member functions, and non-const objects can also call const member functions. So this will compile fine, 308, and this will run fine for us. It'll print out Chris because we set the name to Chris and we printed out the name of that object. Watch what happens though if I try to, in my get name, do something like change name, like sneak it to Matt, like this. If I try and set it to be Matt, what you'll notice is because this is a const member function, we'll get this error. Now this error is a bit tricky to read. It says no viable overload for equals, and then it says candidate function not viable. This argument has type const standard string, but method is not marked const. So what this is saying here is that that this argument, in this case, is expecting it to be these compile errors are really confusing. It's basically just saying like it has no idea how to deal with this because you're modifying something, right? And you can kind of pick up on these pretty quick because the compiler will like highlight it for you and give you like a roundabout error. If I remove the const on this though, let's see what happens now. Maybe it still won't work. Okay, so this one worked, and the reason for that is because without the const, this function is allowed to modify things. With the const, it's not allowed to modify things. Const functions can be called by anyone. They can be called by const persons, they can be called by non-const persons, it's totally fine. Non-const functions though don't like being called on const objects. So here I have a const person who I set the name as Chris, and then I try and get the name of that person. Now set name here is the one that's not const. Right? It makes sense. We need to modify the name. It's actually going to mutate something. The function needs to be not const. There's no way around that. But this won't compile. Const functions are only for classes, yes. And this is, we'll get a similar thing here. This argument to member function set name has type const person. So basically what it's saying is this refers to the object. So it's kind of like the object of member function set name has type const person. It's like, it's a const thing. I can't call this because it's not const. So the implication of this is when you're creating member functions in your classes, all of your member functions should be marked as const, always. Unless they can't be, because they're mutating something. And the reason for that is because if they're not marked as const, our const objects can't use them, right? Like if you just didn't have this here, right? If you got rid of that const, and you weren't even trying to set the name, you were just trying to print it out, something fairly harmless, this wouldn't work because the compiler would say, sorry, I'm a const object, and this is a non-const member function. So we always define our member functions as const, unless we can't. That's the kind of rule here. Where things get more complicated, as we'll see in assignment 1, is sometimes you need a const and a non-const version. We'll talk about this more next week with operator overloading, but sometimes you actually need 2 copies of the same function, one for const and one for not const. But that's kind of enough to start const off now. What do we got left? Okay, two more rows. Static members and deleting unused member. Okay, this is fine. We'll probably finish up really close to 8. Maybe a few minutes after. We'll see how we go. So next thing is this idea of static members. And I'm assuming that you're familiar with what static is from previous courses that you would have done or anything to do with OO. Static members belong to a class, or they belong to every object, whichever way you like to think about it, right? Every object or the class. And they don't belong to a particular object, because normally every single object is created with its own data members, and then those data members belong to the object. The more functional way to think about statics, though, for a given class, is they're essentially just global variables that are inside the scope of the class, and you treat them like global variables, and you kind of define them like global variables as well. Static data members, or static functions, but I guess more so data members, they also have a global lifetime. So they exist from the beginning of the program to the end. Because they're not attached to a particular class, they don't have an object lifetime. So they just exist as long as the program runs. So what we have here trying to remember why there's two of them. Why is there two of these things? Oh my god, it's like playing spot the difference with myself. I see an extra line, but oh yeah, sorry, dirt. I'm really silly. So, yeah, static. Maybe I should have looked for the static keyword. So here, on the left here, this is without static. So let's say you were making a class for a user, right? You had a user class that defined a user, and you wanted to have the ability to check if that username is valid. So what you might do is you might create a function called validName that takes in a name and it tells you whether it's valid. Right now, there's better ways to do that. But let's say you wanted to do that. You thought you put it in the class because it's related to the user, right? You could make it a global function, but then it's not organized as well. So you put it inside your class. You made it a public member function. Now, with that, this is how you'd call it, right? You construct yourself a string called Santa Claus. You construct yourself a user, sorry about the indentation, here. And then you say, if the user objects, then you call the validName. So validName is a member function of the user object. If the name here, Santa Claus, the string, is not valid, if it is valid, then we construct a user. On this side though, what we've done is we've used a static type. Now the reason you should use a static type here is any time that your function does not rely on a data member of the object to process, then it doesn't need to be a member function. It can just be a static function. So while we're checking if the name's valid, we're not actually using the name inside the class here. So in this case, it's static. Now, what does that mean? That means it's not tied to the object. It just means it's tied to the class. So the actual definition is pretty similar. But what's less similar here is that when you call it, instead of doing u dot, because you're doing an object dot property, here we do user : : Remember how I said before that static functions are essentially like global functions that are scoped inside the class. So you call it as if it's a global function, but it's inside the class scope, and the class is called user. So that's how we use static member functions. You can define static member functions inside the class or outside the class, but what's a lot more common to interact with is static member fields, or like data members, you might call them. So static member fields are usually declared, or I should say they're usually defined. I should probably like update that language. They're usually defined outside of the class scope, and we explore this more in your tutorial. I remember why I left that now, because we did that in the tut. So how do you create a static? Like, what do you do if you want your string to be static here? Like if you want your string name to be static, well, you put static out the front of it. How do you define it? How do you use it? Well, that's covered in the tutorial this week. If you're going to skip your tutorial, mine's recorded. I halfway through uploading it before this lecture, so it'll be up tonight really quick. And yeah. I think just another thing, this just randomly occurred to me, but sometimes you'll hear me be like, oh, that word should be something. To be honest with you, a lot of that actually comes from like, the more you spend time with a language like C++, the more you realize how powerful language is in communicating stuff, like talking about constness or non-const or objects or classes. Like you'll hear a lot of students, right? You know, they'll use classes and objects interchangeably. They'll be like, oh, you know, I created a class here. And it's like, you didn't create a class, right? So, yeah. Anyway, my point is like, that's why you'll see some random updates, because sometimes it'll just click for me that like I've done the same thing we all do, where we say declare when we mean define, or objects and objects, instances, classes. And I think language is really awesome, and I think that's one thing that actually helps separate like a good software engineer from a great one. So the last thing we'll go through today, remember this is in the tut, you can go look at the tut for this. It's question 4, the solutions are released on Friday night. It's not related to assignment 1 at all, so don't stress. The last one is deleting unused default member functions. And this is kind of a really interesting one, because we said before about synthesized constructors, where if we have a class like this, like an infec, okay, and I think I have an example of this that we can talk to. Yep. So if we have a class like this, infec, and you can see that we've created ourselves an explicit infec constructor, where it takes in a length, which is of standard vector int size type, and then it initializes a list, constructs that vec using that constructor we saw before, where you give it the length and the 0. We're using the parentheses here instead of the braces because otherwise it would mistake this for constructing a vector with 2 values as an initializer list, whereas here we're trying to say, no, I want to call the function that takes in a size and then the type. So this will create length zeros. Now, because I created this constructor, the compiler, if you remember before, will not synthesize another constructor for me. Okay? It will, it will essentially not. Remember how we said that if you don't define any constructors, the compiler will synthesize one for you? Here it won't do that because we've actually created one. So what that means is that for this code here, this will compile because I create a vector, and then I create an infec, which gives the size of that vector. And when I go to actually compile this one, demo 311, oops, it will do nothing because I did nothing, but it will compile because it's valid. But if I try and do infec BA here, which is a little bit on the copy constructor side from last week. In fact, I might even just try infec B like this, like a default constructor, right? Oh, I've already got that above. Sorry, here it is. That's where it is. So if I try and just create an infec with no parameters, what happens here? It doesn't compile, right? Because the compiler does not automatically generate for me a constructor because I defined one. But we can actually fix that, funnily enough, by doing this. We can say infec brackets equals default. Now, if you say a constructor is equal to default, right, then what happens is the compiler will essentially synthesize one for you. So it's kind of like reversing their decision where you're like, the compiler's like, oh, what's it doing? Oh, redefinition of A. Where the compiler's like, oh, I see you made a constructor. I won't create one for you. And you're kind of like, oh, actually, no. I want you to create one. Please do it. So this will actually force the compiler to create a synthesized constructor. That's kind of what that does. And then similarly, just to, I guess, really ring this out, sometimes the compiler will create other types of constructors for you. Like this one is a copy constructor. So we haven't talked about this, and this is very much a week 5 topic. But essentially, for most classes you create, if you give it one parameter that is the exact same class type, it will often just immediately be like, well, I'm literally just going to take that, I'm going to take all your members, and I'm going to copy everything. That's what it'll try and do. But in this case, it's like, sorry, I am not going to exist because I think because we made a constructor too. I think that's how this works. I'm not hugely across this one. No matching constructor for infec. A is a vector. Oh, it needs to be C. It needs to be another infec. Sorry. It can't be a vector. It needs to be an infec. That's the problem. I tried to pass a vector into it instead of my custom class. But then here, when I run this now works. And in fact, I wonder if I needed that. Let's try that out. So let's see if I needed that extra line here. So what you can see is, that's how I thought it would happen. I was confused. Is that when I said before that when you define a constructor, the compiler doesn't create any other default constructors, it actually just doesn't create the literal default constructor with no parameters. But what it still does do automatically is it will actually create other constructors like the copy constructor. So without ever specifying this, your object is able to be constructed by an object of the same type without you having to write anything. It is synthesized for you. If you want to tell the compiler to not allow that to happen, which there are some cases which we'll talk about in week 5 where that's the case, you can actually, instead of saying default, you can kind of say delete. So default and delete are the keywords that allow you to kind of instruct the compiler how to tweak its manual, like its automatic behavior here. So delete saying, no, 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 don't let anyone do this. Don't let anyone copy construct this. And therefore the compiler will fail this because it says call to deleted constructor. So the compiler is saying, hey, this constructor was deleted. You're not allowed to do this anymore. Yeah, and that's pretty much it. So 757, pretty much wrap up there. There's a demo 300 you can play around with. That's also some more class stuff. You can try and implement some things if you want, but we're not going to go through it in lectures. It's an older example, so the style's all different. We just threw it here because it was around. Like, it's not like core teaching. It's just if you want some extra stuff. Yeah, and that's it. So you don't need to, you shouldn't use classes for assignment 1. That would be grossly overcomplicating it. Assignment 1's just a function. Classes would be overkill. Is there a difference between copying with auto A equals invex C and auto A equals C? So really quick, if I just did this, then without getting into the specifics, I think this is, Nathaniel knows. Nathaniel's a genius if you haven't seen him on the forum. This is either copy construction. This is either implicit copy construction or it's copy construction. Yeah, I think it's just implicit. I think if you put explicit out the front, it might not work. I'm not sure. You could play around with it though. But that's the general gist of what it is. Anyway, cool. Thank you everyone. I hope you have a good night, and I'll see you on Monday. It's a really short week, isn't it? But good luck with your assignment, and I'll send you an update on the weekend. And go to your tutes because it's interesting. So have a good night. Thank you everyone.